morning you had a good introduction regarding what are stars, and then related to the star development, what are neutron stars, not superstars, but in the field of high-energy physics or even in astrophysics, neutron stars are a part of superstars because people are all curious about that, and they would like to study more and more on that front. They would like to know more about it. So naturally, it makes it also a neutron star, a kind of superstar. So, and then how do we catch it? This is the way. I've just shown a cartoon that a man is trying to catch something, and we will see what this man is and what it is there in his hands. Maybe some guesses already you must have made. So we will be discussing about the big and advanced detectors and to catch these neutron stars. Okay, I'm from VCC, and this entire talk is related to the compressed organic matter collision matter experiments at FAIR, and we will see in a moment what all these things are. Okay, so the previous speaker in the morning, he gave you full idea about what neutron star is, so I will not go too much into the depth of it. So I will just remind you typically some of the parameters that this neutron star is typically about size of a city, something like 20 kilometers or so, and it weighs around 1 million times more than the whole of Earth. So these are the estimates. And technically, it is no longer a star. The previous speaker had also mentioned that. And it is a phase that some stars reach at the end of their existence. Okay, the gravitational force is just enough to keep all the neutrons rotating in form of a shell or something. Okay, if the gravitational force would have been large, then it would have turned into a black hole. Okay, so the previous stage is the neutron star for large stars. Okay, while small stars, when they explode, they don't form; they just form small fragments. They don't form the neutron star. How are they detected? Maybe you test that or not, but I can just brush upon a few of the main properties. So as we saw that this has intense gravitational force, which means light coming from there, from the neighborhood or from the vicinity, will be kind of bent. So the astrophysicists or they have kind of really done such experiments and have found the presence, okay, using the signals related to this. And then there is pulsars. In fact, the first neutron star was detected by Jocelyn Bell Burnell in 1967 and on the observation of pulsars. So what are pulsars? These are just these are enormous gravity and fast rotating objects, and then they stream electromagnetic radiations. Okay, so I see all of them are technically qualified to understand this, so I don't want to go into school level details and explain. And then this pulse, as it spins and then points towards the Earth, then you have rapid radio wave pulses by which you detect, and then you have the information about the neutron stars. Do you know how many neutron stars are there? It's about 100 million, and this estimate is based on the number of stars that have undergone supernova explosions. Okay, so something like 100 million neutron stars. This also makes the first case to understand deeper what is inside this and what are its properties. The densities, okay, the densities inside a neutron star far exceeds anything found here on Earth. The positively charged protons and the negatively charged electrons, as the previous speaker had also described in the morning, they basically decompose of atoms, and these are literally crushed together to form neutral neutrons, and that's the name. Okay, so when the neutron star comes, the name comes mainly from there. So what are we going to study? I mean, if I say that we would like to study more and more of the neutron star, so very much, and also when I say what are its properties, so what properties? So as a school, from school way of learning, we know properties of matter. Okay, so what do we know about that? So we know that it exists in 3 states, solid, liquid, or gaseous state, and then these states depend also on temperature. And then they also depend on pressure. Because water, if it boils at 100 degrees Celsius, okay, so at normal pressure, if you go to mountains, then it boils at lower pressure. So these are very, very, very basic properties regarding state of matter. And in a very similar manner, in similar line of thinking, we really want to study the equation of state. This variation, this study of pressure, volume, and temperature forms a part of equation of state. So we really want to study the equation of state of this high dense matter which exists in the neutron stars. That is one of our main interests, which we cannot normally do from these signals or those pulsars and those things which we have kind of detected. Okay? Not so precisely. Okay. So that means the question is, what happens right at the star's core where the density is highest? Okay? Do neutrons dissolve into kind of super dense elementary particle soup of freely moving quarks and gluons as predicted by physical models? We don't know. Okay? So this theory can be tested in an experiment in FAIR, which is known as CDM, which is compressed dynamic matter experiment. Okay? And this will create such highly compact matter on a tiny scale. So just few slides back, I said that the neutron star dimensions are like 20 kilometers or so. Okay? But here in this experiment, we are going to create the neutron stars of the high dense matter very much similar to that in neutron star at a scale of like 1 nucleon. Okay? Very tiny scale. And how do we do this? We take 2 heavy nuclei, accelerate them, and collide them. So this is a, as you will see, it's a fixed target experiment. So you have a target, and you have a highly accelerating nuclei which has a lot of energies. And the moment it bombards, then for a very tiny amount of time, there is enormous amount of energy which is deposited in the tiny volume. And the entire matter kind of gets compressed, okay, at those energies which we are talking about. Okay? So at that moment, for a very tiny moment, this tiny size of neutron star-like density matter is formed in such collisions. Okay? How do we then know about its presence? Okay, we have collided. So how do we know that such a thing has happened? So we come to the only clue about this transient happening can be given by the numerous particles that are formed in this collision. So the moment collision takes place, there is so much of energy dumped at that point, and then this energy is kind of given out in form of numerous particles and their energies. So our aim is to detect all these particles, their energies, and then extrapolate what may have happened at the collision point. Okay? So that's how the role of detectors come play a role. So can one create such a matter in the laboratory, as I said in the previous slide? Yes. And this is how we do, by colliding 2 heavy nuclei. How do we collide? So we need energy, which means we need accelerators. And this is the accelerator facility, or this is the particular accelerator in FAIR, which is Facility for Antiproton and Ion Research. This is a facility which is coming up in GSI, in Darmstadt, in Germany. Okay? So around 2025, this will be ready, and the first beam will be delivered. What is so unique about this accelerator facility? The uniqueness is in terms of these particles. You see, so many primary particles, the luminosity, the beam luminosity is so high. 10^12 per second, 10^10 per second, 3 to 10^13 per second. What's so special? That till today, no accelerator facility, or not till today, I mean, as of today, no accelerator facility can deliver such high intensity. So that is the uniqueness of the FAIR accelerator. Okay? Now, when we talk about compressed baryonic matter, we talk about the phase transition from normal nucleonic state to a state of coagulant plasma. This is what is predicted in such high dense environment to take place. So how do we express this in our high energy field? Or typically this is expressed in terms of temperature versus net baryon density, bit similar to what we talk about, temperature versus P or temperature versus V diagram in phase transition of water when we talk about. Okay, but here we talk in terms of temperature versus net baryon densities. What does this cartoon mean? Okay, I can, if the previous speakers explain, I can just cut short a little bit. So, which means that if we are operating in a energy range where we get some temperatures of this order, or in a region where the particle has had a maximum stopping, the nucleus has had a maximum stopping at the target, that region corresponds to kind of very high, but otherwise here moderate temperature, and this region is considered to be high net baryon density as compared to this region. Okay? So we at FAIR, we want to create a matter which has kind of moderate temperatures but very high net baryon densities, and this is in line with our expectation that that the environment kind of that exists in neutron star will be created in such collisions. How do we detect them? Through particles, as I said. But through particles, in which particles? The most abundant kind of ions, or what kind of particles? So, the medium which is formed, our aim is to determine the properties of the medium. Okay? So this medium which is formed can be investigated by something called rare probes, and these are basically open charm and charmonia. Basically, this is gypsy and this is bimizone. This falls into the category of zoo of particles which exist in particulator group. But these are really the particles which we want to detect because they carry the information about the collision point. But then at these energies, the production cross-section is very low. So you want to have large number of such collisions to get them in sufficient number. And to have a large number of collisions means you may think of running the experiment years together, or you can think of really increasing the intensity. So years together, maybe a couple of factors is fine, but if it is orders, then it doesn't help. Factors in terms of statistics, okay? So then, so this is where, to detect the rare probes, the high intensity of the luminosity plays a big role, okay? And so these are the typical energies of the beam. So in the lab frame, you have something like 11 HeV for heavy ions for Cis 100, and now Cis 100 and Cis 300 are nothing but two phases of development of this beam experiment. Okay, so in Cis 100, it's our energy, maximum energy for heavy ions goes up to 11 HeV, while in Cis 300, which comes later, we go to for heavy ions up to like 35 HeV. Okay? So, and then, so as I mentioned that these rare probes, what is their, these rare probes are basically, do they have a name? So basically they are electromagnetic radiations, and they, or they have these, not radiations, but basically the particles like, as I mentioned, gypsies or bimizone, and they carry the information. And when you do their mass reconstruction, then since they have passed through this matter which has created, they will undergo interactions with that matter and carry the message of the creation of matter. And they will, when you do the mass invariant mass reconstruction, you will find some kind of a broadening in the masses. This is one of the signals that such an object, such an exotic medium has formed in the collisions. Okay? And people have done simulations how the density, okay, develops with time. So I show here that this is the density, okay, and this is time. So you see it reaches about 1.5, okay, 1.5 in terms of 1.5 Fermi cube inverse. Normal nuclear matter has density of 0.15. So you see, it reaches about 10 times the normal nuclear matter density. Okay, this is from the simulations. Okay, so then this is the layout of the CPM experiment. Okay, this is the place inside this blue box. Here, over here, is the place where the target will be placed, and where exactly the place where this high density material will be created by the collision from the beam, which comes from this side. Okay, so the beam comes from here, it collides here.